Okay guys, well welcome back to yet another lesson for us here in calculus. And today, one of the most important, in my opinion, lessons to help you with integration. Okay, so today we will be focusing on integration by utilizing something known as U-substitution. So essentially, by this point in your class, you have covered the basics of anti-differentiating, right? So how to do the power rule backwards, or just like the antiderivatives of basic trig functions, or like e to the x, things that are, again, basic. If you recall, when you were studying derivatives, that's the exact order that you kind of learn things. First, I taught you the basics of taking derivatives, and then eventually we learned about the product rule, the quotient rule, the chain rule, implicit, and so on, right? More complicated ways to derive. So we have reached that point with integration or anti-differentiation, okay? Here's the news though. Unlike derivatives, for anti-differentiating, there is no such thing as a product rule or a quotient rule or a chain rule. Instead, there are going to be techniques that will allow you to undo the derivatives. In other words, to anti-differentiate. Cool? And one of those techniques we will be discussing today, it's called U-substitution. Okay? So U-substitution will help you with all three of those cases for derivatives. It could be product, it could be a quotient, it could also be a chain rule. Okay? So the best way to understand how U-sub works is to dive straight into an example. So I'm going to show you what that means with this very basic example to begin with. Okay? All right. So the first thing I have here is the antiderivative of this function. Okay? First observation is that if this was a derivative, I do have a product rule between this and this. I would also have a chain rule because there is a cube root here. So here is my hint. Here's how this works. You have to select something to represent U. This is why it's called U-substitution. So here's my recommendation. I tend to focus first on composite functions. In this case, I do have a composite function right here, okay? And I like to let U be the inner function. Now, I'm not saying this is always going to work, but this is a good starting point, okay? So, the inner function for this composite function would be 3 minus 5x squared. Okay, so what you will do once you select a U is you will need to take the derivative of it with respect to x. So I'm going to go ahead and derive with respect to x. So implicitly speaking, the derivative of u with respect to x would be du over dx. And on the right side, the derivative of 3 is 0. The derivative of negative 5x squared would be negative 10x. All right. We're going to do one little extra step. Again, stay with me. As we do more examples, this will start to make sense. I want to isolate du. So what I mean by that is I am going to multiply the dx over to the other side, which would then give me negative 10x times dx. Okay. This is called substitution, U-substitution. So what that means is you're going to utilize substitution to solve this problem. Fine. First things is we'll do is we have a cube root, and according to what we wrote here, we know that 3 minus 5x squared, it's equal to u, so I'm going to replace this with a u, and look at that. Coincidentally, not really, okay, I am getting that the negative 10x dx is equal to du, which means this part will get replaced with a du. Okay. This is a pivotal moment to understand U-substitution. The idea of U-substitution is you find a u such that the derivative of that u is equal to something that you actually already have present here, and you're going to be able to substitute. And the idea behind it is that you're gonna take something that's complicated as a product within a chain rule here into something that's very basic to integrate. And what I mean by that, if you still don't see it, is I can rewrite this statement as u to the power of 1/3 du. If you compare this versus this should now be something that you can anti-differentiate with the basic rules that you've been studying prior to today. So I'm just gonna do the power rule backwards here. So that would allow me to say this is u. Remember, you add 1, so 1/3 plus 1 will give me 4/3. You divide by the power that you obtain, and you add c. We're gonna clean that up a little bit. Divided by 4/3 is the same thing as multiplying by 3/4. U to the 4/3 plus c. But here's the catch. There's no way that the antiderivative of this, or this, in other words, this answer is equal to whatever we got here. This is the antiderivative of this. So now if I want to answer the question, which is the original, let me rewrite it. So the antiderivative of the cubed root of 3 minus 5x squared times a negative 10x dx should equal to, I gotta take my answer and go back in terms of x's, which in your case would be 3/4. Well, u, if you remember, u is equal to 3 minus 5x squared. And in this case, it's to the power of 4/3 plus c, which is a perfectly acceptable answer. There is a way for you to rewrite this in terms of a cubed root. At least for me, I'm totally fine with you leaving it as a power of 4/3. If you really, really want to do this, then I guess you can go and say this would be cubed root of 3 minus 5x squared to the power of 4, and then plus c. Which, again, you could do more, but honestly, I think that's, as far as like what we're trying to teach you here, which is the idea of substitution, I'm totally okay with you stopping at the first step. Okay? So, that's the big idea here. Okay, let me summarize it again. So you're gonna take a complicated expression, find a u such that the derivative of that part actually is something that you actually have present in there so that you can do a substitution. And when you're done with the substitutions, hopefully, if this is going to work, it's going to be something that you can anti-differentiate using basic rules of anti-differentiation. Okay? All right, so that was a great problem to start with. Let's try another. All right, example number 2. Let's go with an antiderivative of x dividing by 7 minus 4x squared to the power of 3 dx. Okay. So once again, let's have an observation here. This is obviously not something that's just basic that I can just anti-differentiate. But again, if I look at it as a derivative, I would need to use a quotient rule with a chain rule in order to derive this. Okay? So once again, I'm going to look into this statement. I'm like, all right, well, I need to choose a u value such that whatever that u is, the derivative of it is present. Now, the hint that I typically give my students, and I'll give to you, is that most of the time, when you do have a composite function, which in this example, again, I do have a composite function. The composite function happens to be down here. I let u be the inside function, which in this case would be 7 minus 4x squared. All right, so I'm going to let that guide me. I like that because I know the derivative of this is going to be something with an x, which is just linear, and I notice that I do have an x up here. So let's see where this takes me. So I know that du is equal to the derivative of 7, so du over dx, is equal to negative 8x with a d, oh, not a dx, sorry, I forgot. I don't want to get ahead of myself. I need to multiply the dx over, which, by the way, as I progress with more examples, you'll notice that I'll tend to skip this step because every single time I'll move the dx over. Okay, so here's where I'm at. I'm gonna rewrite this a little bit so I can help you see it more clearly. I'm gonna put this 1 as a 1, and I'm gonna put this x on the back, so x dx. And then I have a 7 minus 4x squared cubed. All right, by substitution, let's figure out where I'm at. This 1 can stay, this can become u to the 3rd power. Now, I want you to notice something. I have an x dx that I need to replace. But when I did my derivative here, what I actually have is a negative 8x dx. Doesn't match exactly. So I'm going to show you 2 ways to solve this. First way to do it is the following. I need x dx to be exactly the same, so this negative 8 is kind of on the way. So what I'll do is I'll have a division of du by negative 8 equating to x dx. So now this x dx can now be replaced with du over negative 8. Okay? Which then will allow me to, I can pull out, because it's a multiplication, I can pull out a negative 1/8. I'm going to rewrite this 1 u to the 3rd power as u to the negative 3 and have it as a d, which will then allow me to integrate. Now, before I keep going, I said I was going to show you 2 ways of how to fix this. So notice how the only thing that was different between here and here is just a constant multiple. So if you don't want to do this step, the other way that you can do it, for example, is you can go back here and you're like, okay, what am I missing? I'm missing a constant. Make sure that you understand that I'm talking just a constant multiple, not a multiple by a variable, okay? What am I missing is a negative 8. So what I can potentially do is I can put a negative 8 here. However, I can't just add a random number. I can't just multiply by a random number. I want to put a negative 1/8 on the outside. Why? Well, negative 1/8 times negative 8 equates to 1. So multiplying anything by 1 doesn't make a difference. And as you can see now, if I were to do that, now that I have the negative 8x dx, I can replace that exactly with the du, which would put me here. This would become the u to the negative 3, and as you can see, negative 1/8 is still out here. Regardless of the way you choose to go, you will land at the same location. Okay? So now let's just finish up this problem with some antiderivation. The negative 1/8 stays. The antiderivative of u to the negative 3 would be u to the negative 2 divided by negative 2 plus c. This negative cancels that negative. We're looking at 1 over 16 u to the negative 2 plus c, which can be rewritten as 1 over 16 u squared plus c. Now remember, this is the antiderivative of this statement that we came up with, but we're utilizing substitutions to help us solve this. So I can now go back and answer this question, which I can say, well, this is equal to, according to that, let me go this way since I don't have a lot of room, 1 over 16. Instead of u, I need to go back into terms of x's. Remember that we had said that u is equal to 7 minus 4x squared. So then I can say that the antiderivative of x over 7 minus 4x squared cubed dx is equal to 1 over 16 times 7 minus 4x squared plus c. Okay? All right. How are you feeling? Hopefully, after 2 examples, you're starting to kind of see a little bit how U-substitution works, but we're going to do quite a few more examples, so stay with me, okay? Let's try another one. All right, example 3. This looks good. So we're going to go to antiderivative of x to the 3rd plus 1 times e to the power of x to the 4 plus 4x dx. Okay, once again, you can see not a simple antiderivative. I have a product. I actually do also have a kind of like a chain rule type of idea here, again, if it was a derivative. So that's what leads me to believe this is going to be a U-sub. Okay, once again, my recommendation is to first focus on the idea that if you have a chain rule derivative or a composite function, which I do, this would be my composite function, is you're going to let u be the inner function, which is the function that's inside of e to the x would be this. All right, so let's see where this takes us. If I take the derivative, this would give me 4x cubed plus 4, and then a dx at the end. Okay, so let's see where we're at. Notice that I'm landing with a cube, and I do have a cube, but they're not quite the same. I want you to notice that if I had a 4 here, that would give me 4x cubed plus 4, which will match. So that's what I'm going to go ahead and do. I'm going to use that strategy. I'm going to put a 4 there, which would allow me to put a 1/4 on the outside. Okay? So here's what's going to happen. This 1/4 I'm going to write here. I'm just going to rewrite it so you can see it one more time. So e to the power of x to the 4th plus 4x. I'm going to put this in the back and distribute it. So that would be 4x cubed plus 4 with a dx on the back. And I'm going to use my substitutions now. This 1/4 will stay on the outside. This will become e to the u, since u is equal to that. And I want you to notice that all of this, which is what I have here, will become a d. And once again, it has gone from something that was very complicated to now something that is basic. We can now say that the antiderivative of e to the u is e to the u. I do have a 1/4, so I can't forget that. So now, once again, I don't have a lot of room, so I'm just going to say the original problem is equal to 1/4 e to the power of x4 plus 4x plus c. Done. Okay? All right. 3 examples down, probably 3, 4 more to go. Okay, so let's go ahead and move on to the next one. All right, sample number 4. We're going to go with the antiderivative of x plus 1 times the square root of 3 minus x dx. Okay. Once again, I am faced with product, a composite function. I'm going to use my hint again. I'm going to focus on the composite function. I'm going to let u be the inner function, which allows me to get 3 minus x. Take the derivative of that with respect to x, allows me to get 3. The derivative of 3 is 0. The derivative of negative x is just negative 1, so it's going to be negative dx. Okay. Now we've got a completely different problem than what we've been doing. Hold on, because this is all I'm getting. I mean, it seems like I have all this extra stuff, and I didn't really have a way to unlike the other ones, this statement is not really helping me substitute. So does that mean that it failed, that U-substitution doesn't work? Not necessarily. It may mean that you need to do some algebra. I'm not saying this will always work, but we're going to try it, see what happens. So let's see what we can do. First, I'm going to do a substitution. All right. I'm noticing that I need a negative, so I'm going to add a negative here. But if I do that, I have to put a negative 1 out here. Okay, so I'll put a negative there. This x plus 1, right now I don't have anything to replace it with. The square root of 3 minus x will become root of u, and this negative dx will become du. I can't anti-differentiate this right now because this is x's and this is a du. So I need to figure out a way to get rid of that. So, what can I do? Time for some algebra. I want you to notice that this statement right here is u in terms of x. So what I'm going to try to do is manipulate that statement into being x in terms of u. So what I'll do is, if I add the x over and subtract the u, that would be x is equal to 3 minus u. I'm going to be able then to replace this x with a 3 minus u. So that's equal to negative antiderivative that x gets replaced with a 3 minus u. I still have a plus 1 here. I still have a square root of u and a du. I'm like, okay, this looks interesting. I have not been able to get rid of a multiplication. It almost seems like it's the same type of thing. So how did this help, or did it help? Well, let's explore a little bit more algebra and see if it does help. All right, first, I can combine this to become 4 minus u. I'll still have the root u, and I have the du. Still a product. I don't have a rule for products for anti-differentiating. So, can I actually anti-derive this? Well, let's look at the difference between this product versus this product. Can I actually multiply this out from the beginning? Absolutely. You can distribute this into here and this into that. The problem is that I'll still have like a product between these two things. Like I can't actually combine. I want you to pay attention to this one. If I do distribution, let's see where that lands us. So I'll have a negative. This would be a 4 with the square root of u. I'll put the parentheses. And this would be, okay, let's be careful. So how do I multiply u times the root u? Well, I'll write it like this for a moment and then remind you of some algebra rules in just a second. Recall from algebra that a square root can be written as u to the power of 1/2. So if I do that, then it would be u times u to the 1/2. And if you recall from algebra, when you're multiplying and you have the same basis, you can just add the powers. So that would give me 2 negative antiderivative 4 u to the 1/2 minus u to the 3/2 d. Okay? So, let me make sure that fits on the screen, sorry. Running out of room, so let me switch over my camera. There we go. Okay. Can I actually anti-derive this? Well, yes. Now this is just a simple power rule backwards. This is just a simple power rule backwards. So let's go ahead and take care of that. So negative, I'm going to put a parenthesis because that negative will be distributed. U to the 1/2, I would have 4. I would add 1, so that would be u to the 3/2. I'll divide by 3/2. Minus, the u would go to 5/2 now, divided by 5/2. Close my parentheses, and I'll have a plus c. Clean this up before I do my substitution. If I distribute the negative, this becomes negative 2/3 times 4 u to the 3/2. Distributing the negative makes that into a positive, so I'll be 2/5 u to the 5/2 plus c. So I'm going to look at, can I do anything else? Well, it all depends on how much algebra really you are wanting to do. Let me go up here since I don't have a lot of room. I'll go u. Okay. I can multiply this out, and then I would have 8/3, right? So I'll have 8/3 u to 3/2 plus 2/5 u to the 5/2 plus c. Okay. A little bit more algebra again. Not sure how much algebra your teacher would want, but I'm noticing that, for example, what do I have in common between these two is that they both have at least a multiple of 2, and they both have a u to the 3/2. So I can pull out a 2 u to the 3/2 by factoring. Then that means all I would need here is a 4/3. So if I do this times that, it equates back to this, plus 2 times 1/5, and then simply u would multiply back out to this. So now, seems like I have my answer. All I have to go is now back and answer the original question, which then I can say, let me go back and just replace u with what it originally was. U was 3 minus x, so I can say 2. 3 minus x to the power of 3 halves times 4 thirds plus 1/5 times 3 minus x plus c. Again, depending on your teacher or depending on your assessment, you might be able to do a little bit more algebra there, but overall, I think I would be satisfied. If I'm being completely honest, I would have been satisfied here and you substituting back here. Cool? All right. So now we finally encountered something that was a little bit different, right? In this case, we had to manipulate our use statement in terms of to get x, to replace x, and then we were able to do substitutions. So in other words, sometimes it's not going to be straightforward where everything you need is there. You might need to do a little bit of manipulation with algebra. Okay? All right. Awesome. Let me go ahead. I need to get a drink of water. I'm going to pause the video for a second, and then we'll try to... All right. Sorry for that interruption. So let's go ahead and keep going. Here's our example number 5. All right. This one, finally, we're running to an example where we actually don't have a composite function per se. If you want to look at it that way, technically you could almost also look at a composite function here if you're really, really careful. But let's just pretend you don't recognize that this is a composite function. Well, I have a division. When a composite function is not as obvious as maybe the first few examples, and you have a division, my recommendation is to look at the denominator and let the denominator be u. So let's see what happens. U would equal to x minus 6, which would mean the du would be equal to simply dx. Let's make our substitutions. This 4 can stay. X minus 6 will become u, and the dx literally becomes du. All right, maybe at first instance this is not quite obvious, so let me help a little bit and rewrite this. If I put the 4 there, then I can write this as 1 over u du. And during your basic integration techniques, you hopefully were taught that if you have just a number that is a constant that is multiplied, you can pull it out of the integral, which will leave you with just 1 over u du. Okay? A lot of times students get this wrong, and they want to, because they don't recognize it, they want to rewrite this as u to the negative 1 du, and they want to utilize the power rule. Let's see what happens if I use the power rule backwards. If I add 1, I will get u to the 0. That's not the problem. Then I got to divide by 0. Okay, I can't divide by 0. So what does that mean? I'll tell you what that doesn't mean. It doesn't mean that you don't have an answer. But what it means is, like, for sure, can't go in this direction. So maybe you're missing something from the past. Is this a basic antiderivative? And the answer to that is yes. There is a function whose derivative is simply 1 over u, and that is the natural log of x. If you recall, the derivative with respect to x of a natural log of u would be u prime over u. Okay? In this case, since it's with respect to u, the derivative of u will be 1. So that means this is equal to 4 natural log. Now this is new, so let's talk about it. There has to be, when you are anti-differentiating, there has to be an absolute value symbol here. Well, why? Let's talk about it. This function, 1 over u, before I anti-differentiate it, this function has a domain. Let's go back to algebra, such that it is all real numbers except it cannot be 0. Because I can't divide by 0, right? But it can be any number that I want, right? So when I anti-differentiate and I get a natural log, let's pretend I don't have that. I guess then the question becomes, can you take the natural log of any number that's part of this domain? And the answer to that is no. You can't take the natural log of a negative number. So to avoid that, we're going to go ahead and include this, and you can do this for every problem to play it safe so you don't have to check the domains. When you anti-differentiate and your answer is a natural log, go ahead and include the absolute value symbols, okay? So this was a pretty basic examples for this. So now I can go back and say that the answer for this, I'll go this way, is equal to 4 natural log of the absolute value of x minus 6 plus c. Oh, so How we feeling? We've got 5 examples in. We've tried a little bit of quotients, we've tried a little bit of products, definitely a bunch of composite functions. So hopefully by now you're starting to recognize a pattern for U-substitution. Okay, let me check to see if I have anything else before I call it for this video. But I have like 2-3 more problems that I think look promising, that I think you would benefit from on this video. So let's try a few more. All right, moving on to example number 6. This one. All right, so once again, I have a quotient, but this time I think it is a little bit more obvious that I do have a composite function. It's a little bit obvious to see that the inner function is ln of x. So unlike the previous example where I said we had a fraction, so I'm gonna let the denominator equal to u, I'm gonna let the composite function overtake that. Okay, so there's a composite function, so let's see what happens. The composite function is there, which would mean u is ln of x, which would mean du is 1 over x dx. Help you rewrite this to see it. This would be the same thing as saying ln of x to the 8th power times 1 over x dx. Multiply this, I get back to that. Substitution, 1 over x dx would result in a du. This would be u to the 8th power. Anti-derive that, that would give me u to the 9th power divided by 9 plus c, which it would be 1/9 u to the 9 plus c. Allows me to go back and say, all right, well, what is the answer to this? 1/9. U is basically ln of x, so this would be ln of x to the power of 9 plus. Okay, that wasn't terrible, right? Maybe, I don't know, I just want to cover all my bases to kind of show you, U could be on a fraction, it could be on the top, it could be at the bottom, just kind of really hopefully by this 6th example, you're starting to recognize that I haven't mentioned this a lot. When I look at a problem, I look at which part, like if I let u, remember I told you this in the beginning, if I take the derivative of it, do I have that part? I knew it was a little bit hard to see, maybe you haven't done this enough, that the derivative of ln of x is 1 over x, and I can totally see that I do have a 1 over x. Okay? All right, let's try another one. Very similar to the last one, okay? Except that I don't quite have a composite. This is a little bit different. I'm not saying that I have the natural log of x to the 6th power. I have natural log of x to the 6th power. A little bit different, okay? Well, let's look at this. I don't technically have a composite function per se. I do have a fraction, but I don't think that if I let the denominator be all of this, like think about it, if I let u be all of the denominator, to derive that, I would need a product rule. I don't think remember, I want to make u equal to something whose derivative I have. I know I'm not, I don't even want to try. The derivative of this would be a product, which would result in quite a large statement. I don't think that's going to happen. What I'm interested on is the fact that I do see a 1 over x. I know the derivative of a natural log is 1 over x. The problem is that I don't have a natural log of x. I have a natural log of x to the 6th power. So what could I do? Think back to algebra. In algebra, you were taught something called the power rule for logs, which basically stated the following. If you had a logarithm, whatever base, it doesn't matter, base a, of b to the power of x, you could bring the power to the front to rewrite it. Not calculus, it's not a power rule for calculus, this is just a power rule that you learned back in algebra 2. I want to utilize that, see what happens. this will allow me to bring the 6 to the front, so 6 ln of x, where am I x, sorry, dx. So let's see what happens. I'm going to let u be ln of x, because that was my instinct, because I saw 1 over x. Alright, so I see a 1 over x right here, 1 over x with the dx. That can become du. That leaves me with a 1 here. That 6 doesn't have anything to replace it, and then the natural log literally just becomes u. Now remember, I don't feel uncomfortable with this, but if you need to, you can pull out the 1/6. So that's 1/6 integral 1 over u du. Luckily for you, we've already done a problem like this, so I don't have to re-explain that part. We know the antiderivative of 1 over u would be the natural log of the absolute value of u plus c, which now allows me to go back into the initial problem and say the answer to this would be 1/6 natural log of the absolute value of, okay, what was my u? Well, my u in this case is ln of x plus c. A little weird, right? Natural log, natural log. Don't worry about that, okay? Now, if you wanted to, since I use the power rule, you don't have to, but if you wanted to, this can go back into the inside if you want to. This would be natural log of x to the power of 1/6, which if you want to go even further, that would be the 6th root of natural log of x. Okay? All right. I think, no, I lied. Once again, I lied. Sorry. Let's do one more. No, a couple more. Sorry, I haven't done any trick. Okay? All right. Let's do the next one. All right. So example number 8. So we've got 4x divided by x minus 5 to the power of 2 dx. All right. So by now you've tried this a little bit. You can pause the video so you can get this on your own. Okay? So pretend now that you actually tried it on your own. Let's talk about it. I see division, but I also see a composite function. So I'm going to go with my advice from earlier. I'm going to let u be the inside of that composite function, which would allow me to get the du is equal to dx. All right. So where does that put me? The bottom would become u squared. The dx becomes du. But I'm noticing, first I'm going to pull out the 4. I'm noticing that I'm still left with an x. Which reminds me of a previous example. I'm going to go ahead and manipulate this. I know that x will equal to u plus 5. So this x will get replaced with a u plus 5. Okay, we haven't gotten to something like this in the past. I do have a division. The question is, can I actually divide? The answer to that is yes. I can actually divide before I do my integration. This could be u over u squared plus 5 over u squared, put the parenthesis du. Keep the 4, let's keep simplifying before integrating. U over u squared would be 1 over u. 5 over u squared, however, I think it'll be helpful for that one to rewrite as u to the negative 5, u to the negative 2, du. And we're ready to go. Antiderivative of 1 over u would be natural log of the absolute value of u. Antiderivative of 5u to the negative 2 would be 5u to the negative 1 divided by negative 1 plus c. Let's clean that up. This would be 4 natural log absolute value of u. 4 times 5 divided by negative 1, that will be minus 20. And then because it's u to the negative 1, it's over u plus c. We're going to go back and replace our u with x minus 5. So we can go back and answer the question and say that 4 natural log of the absolute value of x minus 5, sorry, let's close the absolute value, minus 20 over x minus 5 plus c will be the antiderivative of the original function. Okay, so actually I decided that for trig I'm actually going to make a different video. However, I am not saying that U-substitution can't help you with trig. If you do run into trig and you still have problems, just keep an eye out. I will post another video that specifically focuses on integrating with trigonometry. But anyways, hopefully after, what was this, 8 examples, you're kind of getting the flow of the idea of how U-substitution works and how powerful it can be, how it can take something that's very complicated with products and quotients, chain rules, and make it into something very, very basic. But anyways, thank you so much for watching, and we'll see you next time. Take care.